A GPU parks 32 threads to hide a 400-cycle memory wait. That swap is the whole trick. The win isn't doing math faster, it's never sitting idle. Watch how it turns waiting into speed. Everyone thinks a GPU is fast because it's packed with thousands of tiny math units. That's the wrong picture. The real story is scheduling around a memory wall. A load from memory can cost about 400 cycles. Get that and GPU speed stops being magic. Start with the difference in design. A CPU core is a genius sprinter. It has deep pipelines, big caches, and branch prediction. Every trick is aimed at finishing one task as fast as physically possible. It's built to win a single race. A GPU throws that philosophy out. Instead of a few brilliant sprinters, it fields thousands of plain runners. Each one is simple with tiny resources of its own. None of them is fast alone. So why bother? Because the GPU isn't trying to finish one task quickly. It's trying to finish the most total work per second. It spreads that across a huge crowd of tasks. That's the split. A CPU has a handful of fat, powerful cores. A GPU has thousands of lean lanes, each doing a little. Speed per lane doesn't matter here. Total flow does. Picture a single-lane highway with a Ferrari. Now picture a 1,000-lane road full of hatchbacks. The Ferrari wins a drag race every time. But move 10,000 people and the wide road wins in a landslide. That's the whole bet a GPU makes. But running thousands of lanes raises a hard question. How do you control that many without drowning in overhead? Here's the trick that keeps overhead low. The GPU doesn't steer each thread on its own. It bundles 32 threads together and marches them in lockstep. That bundle has a name. A warp on NVIDIA hardware, a wavefront on AMD. It holds 32 or 64 threads. Now the payoff. The hardware fetches one instruction and decodes it once. Then it fires it across all 32 lanes at the same time. Every lane runs the exact same instruction, just on its own slice of data. Think of a rowing crew. One voice calls the stroke and 32 oars pull together, each in its own patch of water. One command, many hands. So why 32? Because fetching and decoding an instruction is expensive. Doing it once for 32 lanes spreads that cost thin. Splitting the bill 32 ways keeps the chip both cheap and wide. That's the deal that makes thousands of lanes affordable. But lockstep has a dark side. What happens when those 32 threads want to go different directions? This is where lockstep bites. Say your code has an if-else and half the warp takes the if. The other half takes the else. The hardware can't split the bundle. So it runs both paths one after the other. During the if, the else lanes sit switched off doing nothing. During the else, the if lanes go dark. Same command, many hands. But now half the hands are idle each round. The cost is brutal and simple. A clean 50-50 split can cut your throughput in half. At any moment, half your lanes are disabled. This is called branch divergence. It's where GPUs quietly blitz speed. So the mental model is this. Warps love it when every thread does the same thing. Uniform work is where they scream. Data-dependent branches are the enemy. Each thread decides its own path based on its own numbers. Keep the crowd marching together and the GPU flies. Let them scatter and you've thrown half the chip away. But even perfectly uniform warps hit a wall no amount of lockstep can dodge. That wall is memory. Now the core promise. A single add takes about 1 cycle a blink. But a load from main memory costs roughly 400 to 600 cycles. That's not a pause. Next to a 1-cycle add, a 400-cycle wait is an eternity. So what does the GPU do while it waits? Nothing you'd expect. It does not stall. The moment a warp asks for memory and has to wait, the scheduler parks it. Then it instantly swaps in another warp that's ready to run. That swap is the whole game. It's called latency hiding. And here's the part that makes it work. The switch costs nothing. On a CPU, swapping tasks means saving and restoring registers, real overhead. On a GPU, every warp's registers stay parked on chip the entire time. So switching warps takes 0 save, 0 restore, 0 cost. That's why a GPU deliberately loads far more threads than it has lanes. Engineers call it occupancy. More warps waiting in the wings means more work to hide behind that stall. The chip is never idle because there's always another warp ready. But hiding a wait only works if there's enough real work to fill it. Where does that work actually come from? Here's where it gets tight. Hiding a wait only helps if there's work to hide behind. And that work runs out because of bandwidth, not math. Modern GPUs can do something like 50 to 100 math operations for every single byte they pull from memory. Read that again. The math units are so fast that most real programs sit starving. They wait on bytes to arrive, not on calculations to finish. The bottleneck isn't the maths, it's the feed. So the whole game becomes this. How do you feed bytes as fast as possible? This is where a rule called coalescing decides everything. When the 32 lanes in a warp all read 32 addresses right next to each other, The hardware fuses them into one wide, efficient grab. One trip, 32 bytes. But when those lanes read scattered addresses all over memory, the hardware can't fuse them. It splits into many separate trips, and each one wastes most of the pipe. Same data, wildly different speed. It's like 32 people ordering from one aisle, versus 32 people each running to a different store. One trip versus 32. So the real skill isn't clever math. It's arranging your data so every warp reads in one clean, fused sweep. Now watch the whole chain click. Threads bundle into warps of 32. One instruction fires across all 32 lanes in lockstep. A warp hits a load, faces a 400-cycle wait, and gets parked. The scheduler instantly swaps in another warp for free. The registers never left the chip. Do that across thousands of threads, and the memory system stays saturated. Always fetching, never idle. And that's why bandwidth, not math, is the ceiling. The math units are so fast they're almost always waiting on bytes. So the real job is feeding them. Coalesced reads, high occupancy, a constant river of data. Parking 32 threads to hide 400 cycles isn't a hack bolted on to make up for slow memory. It is the design. That swap, repeated millions of times a second, is exactly how a GPU turns one stream of instructions into thousands of threads running at once. One line to keep. GPUs win by hiding memory weights behind more threads, and bandwidth is the ceiling everything runs into. That's the mental model. Carry it everywhere. So here's the thread to pull next. We parked warps and fed the pipe. But there's a faster shelf right on the chip called shared memory, plus special tensor cores built just for matrix math. And there's the real question. How do you actually write code that reads memory in one clean, fused sweep? That's where we go next.